This video is on radiometric dating. Another one, this one's going to be a little more in depth. And the example I'm going to use is uranium to lead. That's what we call a radioactive decay series. And there are several of them that we use to date different things based on what's, of course, in the sample and depending on how old we estimate it is. If we're way off in our estimate, that dating method may not work. It would give us an erroneous result. If we're close enough, though, that we might be able to confirm our age estimate or be able to adjust based on our work. So, half-life, all right? You can't understand radiometric dating if you don't know what the term half-life means. So I'm going to go ahead and put this on the board. I know you guys have this elsewhere written out that you can review it in slides, but I'm going to go ahead and do this video kind of just like I would if you guys were in class. All right. So I'm going to write out half-life. And no, that's oh gosh, there was an old joke I used to tell. I just forgot it though. So half-life is the amount of time it takes for 1/2, you guessed it, of a radioactive isotope to decay into its daughter isotope. Okay. Now, that radioactive isotope, we call it a parent isotope. Once it decays, it becomes more stable, and we call that the daughter isotope. Okay. But the amount of time it takes for half of a particular sample, whatever your sample size is of that parent to daughter decay series, once half of it has decayed, that amount of time it took is the half-life. Okay. So for all of the different radioactive elements that we use, scientists got to do a whole lot of work before we can ever use it for radiometric dating, so they know, hey, what is the half-life of this particular radioactive isotope? Okay, so for the example I'm going to do now, we're using uranium to lead. There's actually more than one radioactive version or isotope of uranium to lead, but the one I'm talking about, the half-life is 0.71 billion years. Or you might see it in some texts, just moving the decimal here, that's equal to 710 million years. Okay, so what that means is for uranium, not equals to, uranium to lead, which is Pb, I think, uranium lead, to get half of a sample of that uranium that's radioactive to decay into lead would take 710 million years. Okay, so after one half-life of that uranium that we're talking about here, there's other versions, but one we're sampling here, or using as an example here, 710 million years pass for every half-life. In other words, the half-life of that uranium isotope is 710 million years. Okay. Now, why is that important? Well, if we find something that we know had a whole bunch of uranium in it, and now it has just a little bit of that uranium left, but there's a whole bunch of lead, and we know that the lead wasn't there when it was formed, well, we know there's been some decay happening, right? Okay, so a perfect example, it was actually in the movie you guys watched, the documentary, How the Earth Was Made, is zircon crystals. And we know, because we can recreate it, we know that these zircon crystals form with uranium, and lead's not there. Okay, so you've got this radioactive version isotope of uranium present at the formation of these zircon crystals. And over time, those uranium isotopes decay into the daughter isotope, which is the lead, okay? So if we find a zircon crystal, okay, and it has a whole bunch of uranium and not so much lead, we might say that's a more recent, it's a newer crystal, and that therefore the rock that it's in is a newer rock. If there is barely any uranium left compared to the amount of lead that's there, then we know that more decay has happened and therefore more time has passed, okay? So we would say that's an older crystal, and therefore that the rock with the crystal in it is an older rock, okay? So that's the generic. Now you get into the actual numbers. We use that 710 million year number to really work it out. Well, you've got to measure the isotopes in your sample, is what you're going to have to do. So I'm going to go ahead and erase this. And there's a handy dandy chart that you can make, and 2 of the 3 columns are the same, no matter what radiometric dating decay series you're using, all right? So here we're using the uranium to lead decay series that happens to have a half-life of 710 million years. But you could use radiocarbon dating. You could use, oh gosh, what is it? Potassium to argon is one. There's one that's got strontium. Okay, there's a few. I just make a simple chart, table, whatever you want to call it. And at the top, I say, all right, this column will talk about the number of half-lives. This column, I'm going to say, oh gosh, what's the fraction? Okay, we talk about the ratio or comparing how much lead is there versus how much uranium is there to figure out how old it is, right? So we're going to find, if you were to actually do this, the scientists that actually do it, they're going to pulverize the heck out of the sample. They're going to pulverize that zircon crystal, and they're going to run it through a detector that will do exactly what you think. It'll detect and count up the number of uranium isotopes that's still there versus the number of lead isotopes that are there, okay? And what you end up with is a fraction of parent isotopes, in this case the lead, over the total of those 2, okay? So here you have the uranium and the lead, so U plus PB, okay? That's the fraction we want. The parent, again, is just the U, the uranium, all right? So we run it through we pulverize it as, scientists, we pulverize it, we run it through the counter, and it gives us a certain fraction, how many of the uranium and lead, okay? Or maybe it won't give you the total there, but it would give you, okay, here's the uranium, here's the lead, and you'd have to put it in that fraction yourself. You could add up the uranium and the lead, put it in the denominator, just the uranium in the numerator. That's how you get that fraction, okay? And then you'd simplify that fraction down as far as you can, okay? And the numbers we deal with here, I'm gonna make them super simple, I promise, okay? Some of them might be a little harder later when we're doing this further, but this is the first video, so I'm gonna try to keep it simple. So, and then finally, this last category is the approximate, if I can write, age of the sample, okay? So, and remember I said these 2 columns here, aside from the detail about which radioactive decay series you're using, they're going to be the same. The numbers are going to be the same, okay? So after 1 half-life, well, you know what? I'm going to put 0 there. If no half-lives have taken place, if no decay has taken place, we can actually come over here too, can't we? If no time has passed. So 0 is our age. Approximate age of sample is 0. If nothing has happened, if no decay has happened, it'd be 0, right? No half-lives, no age. It's probably undeterminable, honestly, because maybe it'd be a little old, but not enough decays happened, okay? And then the fraction, of course, would be 1 over 1. So 1 over 1, because all of the total would be parents. All of the total down here, the uranium plus lead, it would just be the uranium because there would be no lead. No decay would have happened yet. So you'd have 1 being the number of parents and 1 being the number of parents plus daughters. No decay has happened. So you'd have a whole number basically. You'd have 1 over 1. Or if you went and put it through the counter and it detected I don't know 2,053 uranium isotopes atoms in that sample and no lead, you'd have 2,053 over 2,053, which simplifies to 1 over 1. Okay, no time has passed yet. It's a brand new zircon crystal. After 1 half-life, now you've had some time to decay, right? You've had enough time to decay, so much time that you've got 1/2 of your parent isotopes have decayed by that time. Okay, so now you have 1/2. In other words, you have an equal amount of parent and daughter isotopes in that total. One of each. Okay, the equal amount. This fraction could be 1,000 over 2,000. Could be any number as long as it breaks down to 1/2, meaning that for every 2 parts, for the total, 1 part of it is the parent isotope still. But the other part of it has decayed. And what's the approximate age of the sample? Well, we're using uranium to lead series, the one that has a 710 million year half-life. So once we've had 1 half-life, we run it through the counter, the sample, and we get a ratio or get a fraction of 1/2. We know 710 million years is the age of that sample. That zircon crystal's 710 million years old, which means that the rock that it is a part of is 710 million years old. All right, let's continue. If 2 half-lives have passed, you'd end up with, well, what's 1/2 of a half? If in 1 half-life, 1/2 of the original parent isotopes have decayed, well, now you've only got 1/2 that much of the original material, and another 1/2 of that decays. What's 1/2 of a half? Well, 1/2 of a half is a quarter. Okay, so at this point, you're running your sample, you pulverize it, you run it through the counter, and you get back 1/4 of the parent-daughter decay series isotopes are still the parent isotope. 3/4 of what had started as lead has at that point decayed to, has started as uranium, almost got me there, has decayed to lead. So 3/4 is now lead. Only 1/4 is still uranium, okay? So we've just added another half-life, so we're just going to add 710 million, so plus 710, okay? So we'd have 1,420 million years. Or you might write that as 1.42 billion years, okay? So again, if you come to a sample, you pulverize it, run it through your counter, and you get a 1/4 for your parent to total isotopes, that means that sample, the zircon crystal, was 1,420 million years old, or 1.42 billion years old. Cool thing is we found zircon crystal bearing rock much older than that. Okay, so let's do another one. So if you have it, if we go to 3 half-lives old, you'd be at 1/4 of that original uranium now has, did I say a quarter? Man, I'm just full of brain fart moments. So only 1/8 of the original uranium is still uranium. The other 7/8 has become lead. And that 1 more half-life has taken place, so you're just going to add another 710 million years. So now you'd be at, oh gosh, what would that be, 20, right? 2,130. Am I doing that math right? 3, 11, yeah. Million years old, or 2.13 billion-year-old rock sample. That's pretty cool, okay? And if we went to 1/16th, so 4 half-lives, you'd just add another 710 million years, okay? So that's how the math works, okay? As far as the simple version, where if you were lucky and you got a fraction that landed right on 1/4, that's how you would do it. In the next video, I will break down for you, well, what happens if we get a fraction, after we pulverize it, after we count it all up, what happens if we get a fraction that falls somewhere in between? It doesn't fall right on 1/4. We don't know that it's exactly this or approximately this. How do you do the math there? So the next video we'll do that. So hopefully in this video you understand that the uranium to lead decay series is one of them that is relied upon by scientists to determine the age of rocks that contain zircon crystals. And the whole way it works, you have to know the half-life of that uranium parent isotope. And then, of course, you can just do this very, very simple math. And if you had a sample that landed on one of these, you'd know the approximate age of that sample. And in the next video, we'll figure out, well, what do you do if it doesn't land right on 1/2? Maybe it's in between 1/2 and 1/4, or in between 1/4 and 1/8, or in between 1/8 and 1/16. How do you figure the approximate age then? So that's what we're going to do next. Thank you.